All right, welcome to first video for Unit 2. Let's go ahead and dive right in. Um, Unit 2 is on the molecular and ionic compound structure and properties. Um, what this means basically is that we're going to be talking about molecules and ionic compounds, both of which are materials or substances that involve chemical bonds. We're going to be looking at their structure and then properties of those substances as well. And as we'll discover, structure and properties are sort of tied together. Properties arise due to the nature of a substance's structure at the atomic level. For today, we're just going to be talking about the types of chemical bonds. We're not even going to get into all the different types, but we are going to sort of introduce ourselves to the idea of bonding and we're going to dip our toe into the pool, okay, before we dive in later in this unit. Okay, the learning objective, as you can see, this is quite long, this essential knowledge. The learning objective, though, is pretty simple. We're just going to be explaining the relationship between the type of bonding and the properties of the elements participating in the bond. So, once again, the properties of the elements participating in the bond are going to essentially determine the type of bond that exists. And we're going to be talking a lot about electronegativity. We're going to be talking a lot about valence electrons, polar covalent bonds, nonpolar covalent bonds, ionic bonds, and later in the unit we're even going to be getting into metallic bonds. Don't have time to talk about this in this video, but we'll get there. Okay, so the table of contents for this video, we're going to spend quite a bit of time talking about what a bond is in the first place. Just sort of help wrap our heads around the idea of a chemical bond. We're going to talk about electronegativity, how electronegativity and the differences in electronegativity between two elements can determine whether a bond is ionic or covalent in character. And then we're going to talk about bond polarity and dipoles. In the problem-solving portion of the video, the next video I should say, I'll be talking about how to predict bond polarity, and we'll be looking at some different dipole moment graphs. Not really graphs, diagrams I should say. So yeah, let's go ahead and get in here. So, what is a bond? Okay, I'm not going to read everything I have here on the screen. I know quite a bit about this myself, so this is mainly just for a lot of what's on the screen in the next few slides is mainly for your benefit if you're taking notes at home. So let's talk about two materials. Okay, we have graphite here. This is a big chunk of graphite. Graphite is the same material that goes into pencils. So pencil lead is actually not lead. It's graphite. Okay. It's like a black, somewhat shiny substance. It's kind of slippery, right? So if you've ever like rubbed your hand over a piece of paper that's got a lot of pencil marks on it, you can kind of feel it's like a little bit slick, slippery. So it's actually used as a lubricant as well. It's a good conductor of heat and a good conductor of electricity. It's used in a lot of electronic devices as a result of that. Okay, so we've got graphite. We also have diamond. Diamond is very different from graphite. It's a clear solid used in a variety of different things due to its hardness, right? You've probably heard that diamond is a very, very hard material. Not necessarily tough, so it can break under certain circumstances, but it actually is the hardest naturally occurring material. What's the difference between hardness and toughness? That's too complicated to explain in this little intro slide here, but diamond is the hardest occurring natural material. It's a good conductor of heat, but it's a very poor conductor of electricity. So these two substances have different properties, right? They have a different color, they have a different texture, and they have different properties in terms of like whether or not they conduct electricity, right? Here's the thing though. Both of these materials are made up of only carbon atoms. Okay, so graphite is 100% carbon. Diamond is 100% carbon. So how on earth are these so different, right? Well, the answer is bonding. Okay, the way that the atoms are bonded to each other, the way that the atoms interact with each other, gives rise to this difference in properties, okay? And what I have here are two diagrams that show you what these two substances look like at the atomic scale. This is a good representation of graphite. The carbon atoms in graphite are, they exist in sort of different planes, almost like different stories of a building. The carbon atoms in the same plane are bonded to each other relatively strongly, but the planes themselves are not held together by any real strong bonds. They are held together by weak intermolecular forces, but they're not held together by like a strong covalent bond or an ionic bond or anything like that. As a result, okay, with graphite, this is why it's a good lubricant, okay? This is why it's good for pencil lead, okay? When you take your pencil and sort of scrape it across a piece of paper, what is actually happening is you are scraping off the layers of carbon atoms, right, onto your paper. You're transferring them from your pencil onto the piece of paper, right? And think about it, a lubricant is supposed to like help things like rub past each other, right? Well, if you use this type of material as a lubricant, these sheets of carbon naturally do a good job of rubbing past one another. So it's a very good lubricant because of that. Now, in contrast, diamond, the carbon atoms in diamond, these are held together differently, okay? So they're bonded differently. In graphite, you can see here each carbon atom is only bonded to 3 of its neighbors, right? In diamond, carbon is bonded to 4 neighbors, okay? So actually that's the most bonds that carbon can make, really. We'll learn more about that later. But carbon is essentially like fully bonded in diamond. What ends up happening is you get this sort of like large scale pattern of tetrahedrons or tetrahedra. And so it's like very compact, very dense, and this is what this pattern here that we see is what is how diamond gets its hardness. I have a cool little thing I want to show you. If you go into the notes and click on this picture, there's a link to a Wikipedia diagram. It's a 3D model of carbon, and you can actually spin it around. It's pretty cool. You can see how no matter how you look at it, you can kind of like give rise to these patterns, right? So it is like sort of an infinitely repeating crystal structure. It's very cool. You can like line them up and you can see how this could repeat on forever and ever and ever. And yeah, once again, this is why diamond acts the way that it does, right? You could not easily like slip any part of this past itself, right? With the graphite sheets, you can like slide them past one another because they're not strongly bonded to each other, but in diamond that is not the case, okay? And so that's why it's a very hard and relatively tough material. Okay, so the answer all boils down to the bonding, right? The properties of the materials are different because the structure of the material is different. Even though the matter is the same, right? It's all carbon atoms. It's the way that they're arranged and the way that they're held together that gives rise to the properties, okay? So in chemistry, when we study matter, one of the things that we're most concerned with is the properties of matter, like how it behaves. And we have to understand how things are bonded together, how things are arranged, the structure, in order to really understand that, okay? So here are some bonding basics, all right? First of all, bonding is complicated, okay? We are not going to be able to master bonding in this 1 year of chemistry. It is extremely complicated, okay? But we're just sort of we're going to start simple, and we're just going to try to build up as much as we can, as much as we need to for this course. But it's not something that even I fully understand. There's parts of bonding that I learned today while I was putting together the slides for this video. Here's a simple definition of what bonding is, okay, or what bonds are. Bonds are forces that hold groups of atoms together and make them function as a unit rather than as individuals, okay? And here's a brief list of the types of things that we're going to be exploring as we learn more about bonding. We're going to answer questions like, why do bonds form? and what types of bonds are there? We're going to get to some of that today. How can we measure the strength of certain types of bonds, right? So are certain bonds stronger than others or weaker than others? The answer is yes, and we'll start to get a little bit of a look at that today, but mostly that's going to be down the road. And then you can see that last bullet point there, which I've already started talking about. We're going to be able to explain how chemical bonds at the atomic scale of substances give rise to the properties of those substances at the macroscopic scale. So how things behave in sort of human life really does depend on the way that the atoms are arranged, how they're connected, how they're bonded together at the atomic scale. Very, very cool, interesting stuff. Okay, so let's talk about that first question, right? Why do bonds form? So we actually looked at this situation in the last video, right? Sodium and chlorine. Sodium chloride is composed of sodium cations, or positively charged ions, and chloride anions, or negatively charged ions, right? We already discovered why the electron from sodium moves over to chlorine, right? It's due to those electrostatic forces that the electron feels when the two atoms interact or get into close proximity with each other. So we know why the atom moves over, why the electron moves over, right? That's that electron, that valence electron in that third energy level that hops over, right? Because it feels a stronger pull of the chloride or chlorine nucleus. The question is, though, why did the ions then, the sodium ion and the chloride ion, why did they stick together, right? Why are they bonded, right? So this is a bond that's formed. What keeps them together? We talked about this a little bit last time. The answer essentially is kind of the same. It has to do with these electrostatic forces. Okay, so we've talked about, sorry, this stupid thing down at the bottom keeps popping up. We've talked about Coulomb's law, right? How if you have two charged bodies, they're going to feel a force towards one another, if they're positive and negative, that is, right? So if we have a positive sodium ion and a negative chloride ion, they're going to be attracted to each other, right? So it's all about the electrostatic forces in this case. So why do bonds form? Question mark. A simple answer could be stated like this. Bonds result from the tendency of a system to seek its lowest possible energy. Those of you that had me last year probably remember me talking about something like that. Okay, so I'm going to read that again. Bonds result from the tendency of a system, the tendency of nature, to seek its lowest possible energy. Okay, and the system, in this case, the sodium and chloride ions, the system can achieve the lowest possible energy by behaving in this way, by attracting towards one another. You can think of it, if you look at this form of Coulomb's law, the energy version, right? So it's not the force version where you have the r squared in the denominator, like you can see down that direction. Okay, it's the energy form. It's the energy is equal to K times Q1 times Q2 over R. Okay, it's essentially the same thing though, right? Well, think about it, right? If you were to plug in the values of these charges, right, +1 and -1, that means that the energy is going to be negative, right? And if we want to make as big of a negative number as possible, right, so as negative as possible, we want the energy to go down, right? Then if we reduce the distance, right, if we make R very, very small, then the magnitude of the energy goes up. But it's a negative number, right, because it's +1 times -1. I'm getting kind of in the weeds here, but all you need to really understand, right, is that if you have a positive and a negative object, they're attracted towards each other, and it would cost you energy to keep them apart, right? The natural thing that's going to happen is that they're going to be drawn towards one another. Now, that can't happen forever. They're not going to, like, overlap each other and become the same thing, all right? And that's because when they get close enough, they actually start, like, pushing away from each other, right? Think about what atoms are made of, right? At the center, there's the nucleus, positively charged, and on the outside, you've got the negatively charged electrons. Look at this situation here. When the ions reach sort of this happy medium, right, you've got the positive ion and the negative ion being attracted to each other. If you try to force them much closer than this, then you end up encountering repulsive forces. The electrons on the outside of the ion start to push away. They're getting a little too close to comfort. And the nuclei at the center of each ion start to push apart from each other as well, right? So these big dense nuclei at the center of each ion, two big positive charges, they can't be squished too close together, right? Or else they're going to really start pushing apart. And then also the electrons on the outside of the ion, they're also only going to want to get so close, right? If you start crushing them together, they're going to start repelling. So it's a balancing act, right? They are attracted to each other, right? And that's what causes them to get closer and closer. This x-axis here is like the measure of the radius. So they start to get closer and closer, but they won't get any closer than sort of a happy medium due to the repulsive forces, okay? And so you end up with a reduction in energy overall at that happy medium situation. Okay, so ionic bonds, how and why they form, are relatively easy to understand, right? It all boils down to those electrostatic forces, right? But what about other types of bonds? What are they, and how are they different from ionic bonds, right? Well, it all comes down to electronegativity, okay? And actually, that's not entirely true, but for the remainder of today, we're going to be talking a lot about electronegativity, okay? If you took chemistry last year, you should kind of know what this is. I know we definitely talked about it in my class. Electronegativity is it's like a property of an element or of an atom. It's defined as the ability of an atom in a molecule to attract shared electrons to itself. You can think of it as a measure of how well that element pulls on electrons. Okay? It's somewhat related to the concept of electron affinity, okay? Except electronegativity is only talked about in the context of a chemical bond, okay? So you could talk about the electron affinity of some single atom. You wouldn't talk about electronegativity of a single atom. You would only talk about electronegativity when you have two or more atoms engaged in some sort of bond, right? Because it's their ability of an atom in a molecule to attract shared electrons to itself, so like shared between two different atoms. The electronegativity values are called Pauling electronegativity values. This link right here will take you to a table that has electronegativity values on it. I've also posted this periodic table of electronegativity values to the Canvas course. Okay, it's in the top module in the resources there, so you can access it there or through these notes. The electronegativity values range from 0.7 to 4.0. Don't ask me why those are the numbers, but those are what they are. A small number means that the element does not pull very hard on electrons. Okay, so it has its ability to attract electrons is pretty minimal. A large electronegativity value, like 4.0, means that that element is very good at pulling on electrons. Okay, that means that its ability to attract electrons is very good, or it is very good at doing that. Electronegativity values roughly follow a generic trend similar to the ones that we saw in the previous unit for ionization energy and electron affinity. And once again, electronegativity, the trend that we see in electronegativity is due to those concepts like effective nuclear charge and distance from the nucleus. I love this next slide. This picture is sort of a graphical representation of electronegativity values. Okay, it shows you how, as you go from left to right across the periodic table, electronegativity values tend to increase. And it's pretty easy to understand why, right? As you go from left to right, effective nuclear charge increases, right? So the positive charge in the nucleus increases, and so those atoms, like fluorine, for example, are better at pulling on electrons that are engaged in a chemical bond than, say, sodium, right? And then it also decreases as you go down the periodic table, right? Not in all cases, right? That's why it's called a general trend. But as you can see, like here, 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 and then even on the far left-hand side, it tends to decrease as you go down, and that's because any electrons that are engaged in a chemical bond are going to be in the valence level. And so as you go down, you're getting that valence level is further and further away from the nucleus, and so you have more electron shielding, and just the general pull from the nucleus is, it's shielded from those valence electrons, right? The further and further you go down the table. Okay, so like I said, here's the values. These are the same exact values that you'll see on that periodic table that I've linked in Canvas and on the previous slide. So, why does electronegativity matter? Well, when two atoms engage in a bond with each other, a chemical bond, the difference in electronegativity between them determines the character of the bond, or sort of like what type of bond it is, okay? If the difference in electronegativity between two atoms is large, okay, so let's take sodium and chlorine, for example, okay? So chlorine has an electronegativity of 3.0, sodium has an electronegativity of 0.9. That's a pretty big difference, right? Especially when you look at the ranges here, right? Like this one's way down here, this one's way up here, right? That difference is what, like 2.1? Pretty big difference in the grand scheme of things. So if the difference in electronegativity is large, the bond that's formed between those atoms is generally going to be ionic in character, okay? So what that means is that one atom is pulling much harder on electrons than the other, right? In this case, it's chlorine, right? Because it's got the higher electronegativity value. What that means then is that electrons, or just an electron, are going to be transferred, and you end up with ions, right? Oppositely charged ions. And then you end up in that ionic bonding scenario. If the difference in electronegativity is small, however, okay, let's talk about two oxygen atoms, like just two oxygen atoms, right? One oxygen atom over here, one oxygen atom over here. The difference in electronegativity between those two is 0, right? It's the same element, right? But we know that O2 is a real thing, right? O2 is what we breathe in. You're breathing it in right now. That's a real thing, right? So that is a real chemical. That is a real molecule. If the difference in electronegativity between two atoms is small, the bond is going to be covalent in character. Okay, covalent means that both of the atoms are pulling roughly equally on the electrons. In the case of two oxygen atoms, it actually is equal, right? The electrons are going to be shared between the two atoms. It's not going to be like, in this case up here, right, chlorine was winning the tug of war, right, because the difference in electronegativity was large. But in this case, right, with two oxygens, the difference in electronegativity is 0, right? So the electrons that are shared between them are going to be like equally shared. And in that case, you form a molecule, okay? And we're going to talk a little bit more about all of this later, but just for right now, let's sit with that ionic in character, covalent in character, right? Large difference in electronegativity, small difference in electronegativity. There is a third case, which I'm going to mention here but talk more about later, if you're sort of in between that, right? So let's say it's not a large difference, it's also not a small difference. The difference is moderate. Then you kind of end up in a sort of middle scenario where you have a polar covalent bond. That's the term, polar covalent. And that really is kind of a middle scenario. I'm going to talk more about this later, okay? Let's talk a little bit about covalent bonds. But first here, yeah, there is a nice little picture. You can find this graphic in your book. It's in Table 8, or it's in Chapter 8, Table 8.1. This just is a graphical way to look at what I just explained, right? If the difference in electronegativity is 0, it's a covalent bond, and it's got high covalent character, okay? So what it means is like the bond acts like a covalent bond. If the difference in electronegativity is large, then you have an ionic bond, which is ionic in character. And that middle scenario, right, if you have a moderate or intermediate difference in electronegativity, you have a polar covalent bond, and you're sort of stuck in the middle, right? You're kind of in limbo between covalent character and ionic character. And in reality, it does kind of act like both. Okay, so covalent bonds. Why do covalent bonds form? Why do they form, right? Well, the answer is it's complicated. Okay, that's what I said at the very beginning, right? On the bonding basic slide, my first thing was it's complicated, okay? And it is. Ultimately, the answer to this question, why do covalent bonds form? Ultimately, the answer is the same as it was for ionic bonds. The overall energy of the system decreases when atoms form the covalent bonds that they do. Okay, it isn't as easy to convince ourselves of this like it was with ionic bonding. Like if I go back quite a few slides here, remember this when I was talking about the balance between the attractive forces and the repulsive forces? This is relatively easy to understand. Okay, ionic bonds are a bit easier to conceptualize and understand like why they form. Covalent bonds, it's a bit trickier, but it is true. It is true that in covalent bonds, the overall energy of a system decreases. The way that we can know this for certain is actually through experimentation. Okay, you can take a chemical, say methane, okay, CH4. This is one carbon with 4 hydrogens covalently bonded to it. Just as an aside, if I come back here and look at carbon versus hydrogen, right, the difference in electronegativity there is pretty small, right? It's not equal, but the difference in electronegativity there is pretty small. So this is going to be a covalent bond that's formed between them. If you try to take methane and turn it into basically methane, but you're ripping a hydrogen away, right? So what you're doing is you're unbonding the hydrogen atom. It costs you energy, right? The energy required is a positive amount, right? And so this can be experimentally determined, okay? So what you can see here is that if you do this 4 times, right, if you rip the hydrogens away one by one, the amount of energy that's required is a little bit different in each case, but the overall amount is pretty substantial, right? It takes you 413 kilojoules per mole, okay, so that's like energy per mole of methane, to take away a hydrogen, right? What that means, right, is that if it costs you energy to take the atom away, then it must be lower in energy to let the atom stay, right? Does that make sense? Like if the atom, if let's say we weren't involved and it was just a carbon and 4 hydrogens just poof, appear out of nothing, they're going to naturally form that molecule, those covalent bonds, because that's a lower energy state. The system there is in lower energy than if they stayed separate, okay? And that's what nature does. Nature tends to move things. Well, move is probably the wrong term, but nature tends to things in nature tend to move from higher energy to lower energy of their own accord. Okay, just like if I take my phone and let go, it's going to fall from a high potential energy to a low potential energy and potentially break in the process. So I'm not going to do that, but you get the point. Okay. Last thing, and I'm trying to keep this relatively short for you guys because I know the 30+ minute videos are difficult to get through. So we got to talk a little bit about that middle type of bond, polar covalent bonds. Okay, so once again, this is just copy and pasted from the previous slide. If the difference in electronegativity is moderate between 2 atoms, the bond that's formed between them is going to be polar covalent, which is really just kind of like the in-between of ionic and covalent. Okay, this is a very common situation actually. Lots and lots of polar covalent bonds out there in our everyday world. You can think of a polar covalent bond as just being partially ionic and partially covalent. Okay, the electrons involved aren't completely transferred from one atom to another like they are in an ionic bond, but they're also not equally shared like in a perfect covalent bond, right? Like with 2 oxygens, they're not going to be equally shared either. So it really is kind of an in-between scenario. My favorite example of this is with water. Okay, so water, arguably the most important chemical on Earth, in the universe potentially. Well, I don't know about in the entire universe, but it's definitely one of the most important chemicals here on Earth. It is made of 2 polar covalent bonds. Okay, H2O. You've got 2 hydrogens and 1 oxygen. Oxygen is sort of the central atom in this, so the hydrogens are covalently bonded, well, polar covalently bonded to the oxygen. The reason that this is a polar covalent bond has to do with the electronegativities. Okay, so if I go back to the electronegativity table, here's oxygen, 3.5, and then here's hydrogen, 2.1. See how that's kind of in between, right? When we were looking at sodium chloride, the difference was 0.9 to 3, right? That was a difference of 2.1. And then when we were looking at oxygen, or say methane, right, the difference here was just 0.4. But when you look at water, you're kind of in the middle, right? You're at, what is this, 3.5 minus 2.1, 1.4. So that really is kind of in the middle of those different situations. What that means then is that with water, you end up with this polar covalent bond scenario, okay? Oxygen is the more electronegative atom, okay? It's much more electronegative than hydrogen. And what that results in is oxygen being kind of an electron hog, okay? So in the electrons that are shared, and I realize we haven't gone into detail of like what exactly it means for electrons to be shared in the first place, but just take my word for it, okay? Electrons are shared here in this bond between hydrogen and oxygen. Electron is going to sort of hog those electrons. It's pulling on those electrons much harder than the hydrogens are, right? I mean, and if you think about it, it's because oxygen has 8 protons in its nucleus, whereas hydrogen only has 1. Okay, so this massive positive charge here is pulling harder on the shared electrons than the 1 proton in hydrogen. Okay, so what does that mean? Well, you end up with sort of more electrons here than you do here. Okay, and if I go to the next slide, this will sort of explain everything, and I think this is the actual last slide. As a result, the oxygen end of the water molecule is partially negatively charged, and the hydrogen ends are partially positively charged, right? Because electrons are negatively charged. So if the oxygen is pulling on the electrons and like literally pulling on, attracting the electrons to where they spend more time with oxygen, then you end up with sort of an overall partial negative charge on this side of the molecule. Whereas the opposite is true over here, right? If the electrons aren't spending time with the hydrogen, then all you have here is a proton. That's it. I mean, that's all hydrogen is, right? It's 1 proton, 1 electron. But if that electron is spending time with oxygen, then really it's just a proton over here, right? So that's why this hydrogen end of the molecule is partially positively charged. This can be written like this, where you sort of draw an arrow in the direction of the negative charge, and then you like cross the positive end of the arrow, so you sort of end up with like a plus sign over here, and then an arrow towards the negative part of the molecule. And then this is sort of like a 3D depiction of the polarity, okay? The red part here is like electron dense, and the blue part is not electron dense. Another way of interpreting this would be the red part is like negatively charged, and the blue part is like positively charged, okay? And green is kind of like in the middle, okay? This is called a dipole, okay? Di meaning two, pole meaning like ends of something, right? So you've got two ends of like a positive and negative charge, okay? And there's a couple of different ways you can talk about this. This is called a dipole. You could say water is dipolar, and you could call this overall concept like a dipole moment, okay? We're going to get into this. We're going to get more into this later, especially when we talk about intermolecular forces in a couple of days, okay? So, like I said, today's kind of bonding basics, sort of getting ourselves acquainted with some of the terms, and really sort of trying to learn about electronegativity and how you can use the difference in electronegativity to determine the different types of bonds that we're going to encounter. Okay? Thanks for watching, and I'll see you on Friday.